So let us take some points on the amino acids and the proteins. Amino acids are the compounds which contain an amino function, we know very well, NH2 function. A carboxylic acid, nothing but the COOH function. You may write as a COOH also. But the COOH is acidic nature and the amino is a basic nature. So the interesting point in this the compound is, it is a compound containing two opposite the property. Even in the carbohydrates we have a two functional groups, hydroxy and the carbonyl, but they are not opposite to each other. They may react, but they are not nullify their qualities. So the acid is the one which is donating the proton and the base is the one which accept the proton. So exactly countering type of the property containing compounds are, the groups are attached to the same compound, may be taken as a bifunctional compound type of the compound. And these amino acids go on polymerize to give the big structured compounds. It is nothing but the protein. So protein may be defined as a polymer of the amino acid. And let us go some amino acids. Amino acids, smallest amino acid. Most of the amino acids will have this particular structure, amino group and the COOH group attached. An example, this is the one example which is taken as a alanine. Alanine will have this structure, there is amino group and the carboxylic acid, and this is the structure of that compound. It may be named as a systematically 1, 2, 3. There are 3 carbons are there, amino group is on the 2. So therefore you can say 2 amino propanoic acid, propanoic acid. So here specifically if you observe the amino group is on the second carbon, or leaving the functional group it comes as an alpha carbon. So it is an alpha amino acid, alpha amino acid. So in the nature it is surprisingly it is identified, there are only so far identified 24 amino acids in the nature, that is in the plants and the animals, in the human body together, and these 24 amino acids all are found to be alpha amino acid. That is the one of the miracle of the nature. Only alpha amino acids are existing in the nature. Their preparation and the successful existence, stability and all that may be related to the position of this alpha. So therefore in the nature we are having only alpha amino acids. Therefore a classification also reveals the same thing. The amino acids can be classified and based on the 2-3 varieties. The first one will be the based on availability or source, where from you get, source or availability. Natural amino acids and the synthetic. Natural amino acids and synthetic. Synthetic means man-made amino acids. There are 24 amino acids identified in the natural. There is no fixed number synthetic. Every day you can prepare some more new compounds, they maybe go on adding. But the natural amino acids, there are only 24 amino acids identified. So second type of the classification is based on the position, based on the position of NH2 group. Like there is a, imagine there is a carboxylic acid leaving the functional group, this is called alpha, beta, gamma, delta and so on. The amino group position, based on the amino group position on the given carboxylic acid, we are going to classify into the 2-3 varieties. The first variety will be the alpha amino acids. Surprisingly, as I said, all the 24 amino acids, all the 24 natural belongs to this category. All the 24 natural amino acids belongs to alpha. So like that you can go for the beta amino acid. The preparation is not that difficult. You can prepare a beta amino acid. An example is the amino will be on the third carbon. 3 amino or the 2, that is beta amino, alpha beta amino. A propanoic acid is a example for the beta, and also like that if you go on shift the amino group to the gamma, delta and so on, different varieties are formed, but only alpha amino acids we find in the nature, so therefore we are interested in the alpha. Similar the way you can classify the amino acids into two more classes also. The third variety is based on the nature of the function amino acid. That is the first variety will be the neutral one, neutral, basic and the acidic. That means in general, if one NH2 group and one COOH is there, the acidity basicity for some extent cancelled and the amino acid behaves as the neutral. But if NH2 groups are more than one, let us say more than one, and the COOH will be specifically only one. In such a case, the amino group dominating the nature, so basic property is attributed, and whereas amino is one group and the COOH will be sometimes will be more than one. For example, here is an example like that. Amino acid will have the amino and the acid, and in addition to that, in the side chain, in the chain also we have one more acid. It is called aspartic acid. Aspartic acid is an example for like that. Lysine is an example for the basic. Huge number of examples are there for the neutral. Similarly, the fourth type of classification is based on the function of the amino acid. In the body, means specifically referring to the human body, they are defined in, they are classified into the two types, essential and non-essential. One more. Essential and the non-essential. Non-essential means it looks like it is not necessary for the human body, but it is also studied that out of 24, 10 is essential and the remaining 14 we can classify as a non-essential. The non-essential amino acid also, if one of these out of this 14 is not present in our body, that leads to some malfunction. So, therefore, they are also literally essential to the body. But the point is here, essential amino acids, non-essential amino acids can be synthesized by the body. So, therefore, this you need not to take in the food, whereas essential cannot be synthesized by the body. Therefore, only the source for this essential is from food only. From food only we have to prepare, that is you have to procure this. From the diet only we are getting this essential. If in our food out of this 10, if one is missing, it leads to give some malfunction of the biological activities. So, whereas this 14, if something is missing, out of this 10, one will be converted into this 14 and that non-essential amino acid, so our body can sustain. So, that is why we are classifying this essential and the non-essential amino acids. Let us take some examples of the amino acid. The smallest amino acid is the COOH, and amino is attached to the one carbon, and this carbon is having a hydrogen as well as the hydrogen. There is two hydrogens, and whereas in the first second example will be this hydrogen will become a methyl group, and so on. The structure of the amino acid goes on, increases, right. So, if the CH2 becomes into a little more extension, a phenyl group, and so on, a series of amino acids are existing in the nature. This is called glycine. This is called a alanine. One need not to be remembered, just to have an impact. I am just giving the names of this compound. This is called phenylalanine. Phenylalanine. Now, if you see carefully, all these the compounds can be summed up with a structure like this, NH2 and CHCOOH with a group. The group you can put a R. R can be a hydrogen, methyl or a CH2 phenyl, and sometimes a butyl, N-butyl, isobutyl, and some little here and there some complicated, but the most of the amino acids will be very simple in their structure. And some compounds, as I said, in the R group also will have COOH, in the R group sometimes NH2 extra amino group. Based on that, basic and acidic properties are reflected. So in general structure will be like this. And if you see carefully, this carbon, this is the only amino acid having no chiral carbon. So this for it is a glycine is a non-optically active, optically inactive otherwise. Optically inactive. These are all optically active because there is minimum one chiral carbon is existing, and it is also observed most of the amino acids will have a common structure like this. The NH2 happens to be in the left side, and so these amino acids are having the L series. But this L will not give any guarantee that the amino acid should have a minus. So though they are L, some are showing the dextro property, some are showing the levo property. Only in the carbohydrate it so happened all the capital D compounds have got dextro property, but there is no the linking property between that DL versus this D and L. This specifically in the amino acids, all natural amino acids are L series, capital L series, because the important group is on the left side, but some of the amino acids are levo, some of the amino acids are dextro also. Okay, right. Let us see one or two synthetic methods, preparations of these amino acids. Though the question on the amino acids so far not appeared like preparation, but these preparations are nothing but the chemical properties of the carboxylic acids and the amines. So therefore, one such method may be using the alpha halo acid method. A carboxylic acid can be, for example, if a propanoic acid, you can go for the alpha halogenation using the chlorine and the phosphorus. This method is called Hell-Volhard Jelinski method. Shortly known as HVZ reaction. HVZ reaction, it is nothing but a alpha halogenation of the carboxylic acid. So using this particular reagent, one can go for the alpha chlorination. And once this chlorination is done, when you treat it with ammonia, ammonia is a stronger base which will replace this Cl, and a nucleophilic substitution reaction taking place, and you will get a alpha amino acid. And this is happens to be a nothing but the alanine. So alanine can be prepared by using this particular method. First you go for the alpha chloro method, then amination. So this is one of the best method. If you take acetic acid, you will get glycine. If you take methyl acetic acid, alanine, phenyl propanoic acid, you will get the phenylalanine, and so on. All the series of the amino acids can be prepared. And another method is also properly, that is more popularly known, is this is a name reaction called Strecker's synthesis. In this synthesis, a carbonyl compound like aldehyde is taken and treated with a mixture of the HCN and the ammonia. In fact, these two can be obtained from a mixture of ammonium cyanide, which in turn we prepare from a combination of sodium cyanide and the ammonium chloride. So these two will generate the ammonium cyanide, which is in equilibrium with the ammonia and HCN. Either HCN or ammonia, either one you can add first. Let us say I will show the HCN addition. O will become OH and a cyanide is added. Afterward, the ammonia will replace the OH. So therefore, either you add ammonia first or HCN add, both the compounds are reacting, and you are getting a carbon with a amino group as well as the cyanide group having one hydrogen. Now you hydrolyze. The cyanide is a triple bond one, hydrolyzed with the acidic medium, and the cyanide is hydrolyzed to acid, and this extra nitrogen goes out. So, we will get a amino acid attached to the same carbon, that is what we want, alpha amino acid. So, this can be prepared by hydrolysis of that amino cyanide, and hydrolysis will give the amino. So, this is both the methods are very simple methods. We have some complicated, but not necessary to refer here. So, two methods which are coming in the one comes from the carbonyl compound chapter, another from the carboxylic acid. We have in fact covered these reactions in that particular chapters also. Let us go some of the properties of these amino acids. The chemical properties like amino function and the COOH function already we have covered in the respective chapters. Like for example, amino group, when you treat it with HNO2, if it is an aliphatic amine, 1 degree amine, they will give the alcohols. So, here also in the same case NH2 is then happens to be an aliphatic, so it gives the hydroxy. For example, glycine if you take and with the HNO2 you will get the hydroxyacetic acid. Similarly, a carboxylic acid will have all the functions properties of the COOH like esterification, reduction into alcohol and so on. All the properties of the acid and amines are restored. In addition, one or two specific properties we will take up here. Specifically in the physical properties, we have one property called Zwitter ion nature. Zwitter ion nature and its applications. This is the one which are having one importance in the number of questions are coming on this particular the concept. Let us take the structure of one particular compound, a methyl group containing COOH and amino acid. This is called alanine. Let this alanine structure A is assigned for this one. Alanine will have nothing but the 2 amino propanoic acid is called alanine. Alanine structure is taken as a simple NH2COOH NH2. But practically thinking what happens, the COOH is acidic in function and this is basic in function. So, therefore, immediately what happens, one proton exchange takes place. From here this side to that side a proton exchange takes place. So, the amino receives a proton, becomes into NH3 plus, and the other side you will get a COO minus. Now, this is the structure of the B, that is alanine structure in the form of B will have a plus and minus. This type of only minus is there, we say anion. Cation is also there. So, let us call this compound as a cationic anion, cationic anion, or anionic cation, or better say Zwitter ion. One atom holding plus minus in a carbon we call carbene, that is totally different. This is a molecule, one end with minus, one end with the plus structure. This is the B structure. However, alanine has 2 more structures. Let us add some dilute acid. What happens, you see? Dilute acid like dilute HCl, if you add, what happens? A proton is taken by the acid, from the acid to this COOH. So, you will get one more structure NH3 plus with CHCOOH, and this structure let us see as a C, and this C structure has got a cationic structure. Now, let us say the addition of acid is HCl. If I take, there will be a Cl minus outside, cancelling this positive charge of the amino acid. So, now if you only talk about the amino acid is a cation. So, let us call this one as a cationic amino acid, cationic amino acid, cationic amino acid. So, that has got the C structure, and if you add the dilute base like a dilute base like an example NaOH is added, it will become into another structure wherein a base, the OH minus is taken out, this H plus, it generates the NH2 free group, and the COO minus still continued. That OH and H will become into water, neutralization, but a cation Na plus will be attached to this anion. Now, our amino acid is having only anion. So, let us call it as a anionic amino acid. Anionic amino acid. Anionic amino acid. Now, let us designate this structure as a capital D. So, therefore, now the question is alanine has 4 structures A, B, C, D. Okay. Let me ask one question. Which of these 4 structures is not suitable for the amino acid? Means we think this neutral will be the more stable one. Actually, the structure A will never exist in our body, because the amino and acid countering properties will neutralize, the B will come. Okay. So, therefore, structure A will never exist. It is only theoretical structure. B, C, D will exist in our body depending upon the acidity and the basicity. That means you have acid means will the pH increases or decreases? As the acid is added, medium will become acidic, means a lower pH. So, at lower pH, the amino acid, that is alanine, exists as a C. So, when you are adding the base, the pH goes up. So, this is at a higher pH. At higher pHs, the alanine exists as a D structure. So, at what pH the deuterion exists? The guess structure is this is lower, this is higher. So, therefore, we think at neutral pH, that means at pH we expect that B will be the possible. But it observed that it is not 7. No amino acid exactly 7 is so far not identified. It is a wrong concept, but most of the amino acids are around 6.1 to around 7.1, that mostly will exist around 6.5 is the average value we are taking. That means beyond 7 also 1 or 2 amino acids exist, but exactly 7 there is no amino acid exactly as a deuterion exists at 7, mostly when 6.1, 6.2, 6.3, 6.4. This pH is called isoelectric point. Isoelectric point. Isoelectric point, this is called IEP, otherwise shortly you can say IEP. So, what is isoelectric point? It is the pH at which the given amino acid exists as a deuterion, or it is a pH beyond that pH, that is in basic medium, above this IEP it exists as a anion, below that IEP the amino acid exists as a cation. That is the type of the pH is called IEP. Now, we have wonderful the applications of this the concept. So, as the pH changes, amino acid becomes into cationic and anionic, and we can also see one of the another property out of the B, C, out of the A and B. Imagine that the A and B both exist. Out of A and B, which will have the higher boiling point, means this is a molecule, this will have the intermolecular forces strong. So, therefore, this will have the higher boiling point, higher melting point, higher solubility also, which is also correct. But A will not exist, therefore, such a question will never come. Now, the comparison is between the B, C, D only. Out of B, C, D, which will have the more solubility? Out of B, C, D, which will have the more solubility, means we think here there are 2 charges, this is only 1 charge, therefore, this will have the more solubility. But practically what is happening, the B will have the minimum solubility, that is deuterion is showing the minimum solubility, that is less solubility, which may be explained as the deuterion is a one which is attached to cation and anion. When it is added to the water, water pulls anion and cation, but it will not able to migrate in the water. So, but that is dispersed in the water, whereas here you see only cation and the anion is separate. So, they are called outer salts, whereas this is called inner salt. Outer salts are free to dissociate or migrate in the water. When this salt is added, that cationic amino acid attached with anion separately, when it is added to the water, the cation goes one side, anion goes in the opposite side maybe. So, therefore, the solubility will be high. So, C and D will have higher solubility than the B. Between the C and D we cannot decide, but C and D will have the higher solubility than the B definitely. B will have a minimum solubility. At a isoelectric point, therefore, a given amino acid shows the lowest solubility. Let us take 1 or 2 questions here. a given amino acid, there are 3 amino acids A, B, C having the isoelectric points. One is having 6.2, the other one is 6.4, the other one is 6.6. These are the pH values of these A, B, C are the different amino acids having these isoelectric points. Right? What do you mean by the isoelectric point? It is the pH at this point A exists as a plus minus. Now, what I am doing is I have taken all these ABC in a flask. I am maintaining the pH 6.4. At that 6.4, the B alone will exist as a deuterion, that means plus and minus structure. What about the A? A needs 6.2, but you are maintaining 6.4, which is basic medium for the A. In the basic medium, what happened? Just now we have seen in the basic medium it exists as a anion. So, therefore, A exists as a anion, right? So, in the acidic medium, so for C requires 6.6, but you are maintaining 6.4, that means for amino acid C it is acidic medium. So, therefore, C exists as a cation. C exists as a cation, A exists as anion, whereas B exists as a deuterion. Now, we have the 2 different concepts or the questions. Of these 3, when I take in a compartment, a vessel which contains the 3 compartments, first compartment, second compartment and the third compartment, they are separated with the porous that is semi-permeable membranes and taken with this ABC compounds, and B exists as I said already plus minus, A is existing as anion, B, C is existing as a cation. All 3 were taken in the middle compartment and then subjected for the electrolysis. So, a current is passed through this the electrodes. The A, B, C are dissolved in a suitable solvent and taken as electrolyte, and then electrolysis is started. The question is now, which migrates into which? Out of this A, B, C, which migrates into third compartment, which migrates into the first compartment? Already we have decided what is the positive charge, negative charge on this anion. So, now this anion goes to the anode compartment. If the anode is this one, will have a positive charge on this electrode. So, anode, that is A is a -1, anion goes to the anode, that means A goes to the compartment 3, A migrates to the compartment 3, whereas C migrates, is acting as a cation, so goes to the compartment 1. Isn't it a compartment? It is migrated because the C is a cation, this is the cathode. Cathode will have a minus charge, so cations will go to this one. So, already we have designated with plus minus, therefore, it is very easy to answer. A migrates to the third compartment or anode compartment, C migrates to the cathode compartment because C is having a positive charge, whereas the B will be stay back in the same compartment, in the second compartment it will stay back. So, this is the fate of these 3 the ions. Similarly, a question also can be framed. The same question we can continue. If A, B, C having this type of the IEP and the pH 6.4, they can be separated using the same technology. Let us take that A, B, C at 6.4. At 6.4 pH, we are going on concentrating, which gives the first crystals. At 6.4, B alone will exist as a B plus and the minus deuterion. So, it will have the minimum or the lowest solubility. Therefore, this starts giving the crystals. B crystals will be forming. Then you collect the B. In the flask you will have only A and C now. Okay? In the flask you will have A and C. Now, what you do is you adjust the pH to the 6.2. So, maintain the flask range as a pH 6.2. So, A starts existing in the now the A will become into the plus minus jitter ion, whereas C continues to be in the anionic cationic phase. So this will have the minimum solubility. So therefore, this when you crystallize it, A alone will get the crystals. Like that, select the pH of that particular amino acid and concentration you start it at that pH, that amino acid exists as jitter ion. So therefore, it will be precipitating or it will be getting as a crystals because of the minimum solubility that crystals will be coming. So therefore, wonderfully you can go for this determination of this, that is separation of the amino acids. Similar the case, if A, B, C are taken separately, when you go for the calculating the conductivity at different pHs, you take the amino acid A and its values of the conductivity at different pH values you calculate. At one pH, A shows minimum conductance or null conductance, that is called its isoelectric point. That is called the deciding a isoelectric point of a given amino acid using the conductance value, because when it is having the plus and minus, its migration cannot be taking place to specifically at anode or cathode. So therefore, the conductivity minimum or null, that is 0 conductance is noticed, that pH is noticed at its isoelectric point. So we have a very good number of applications of this the jitter ion concept. Jitter ions will have a plus minus, therefore it will travel through the different membranes because cation, anion both are there. So that is the one of the transportance of the amino acid through one cell to the another cell. Through this having this particular type of the plus minus structure, it is possible. So we have huge number of biological applications are there, but limited applications we have in the specifically physical properties of this one. Jitter ion will have the lower solubility, therefore separation and this migration, all this we can discuss. Let us notice one more property called pyrolysis. The pyrolysis of the amino acids are very much closer to the pyrolysis of alpha hydroxy acids. Amino acids and alpha hydrox, that is hydroxy acids, otherwise hydroxy acids. You can have a comparison of these two acids. Already these carboxylic acids containing the hydroxy function. The pyrolysis means just heating without putting any catalyst or the reagent, just to go on heat it. A hydroxy acid is there, therefore what happens here? The CO and O of another acid is linked, you get this type of the linkage. So this is one acid, that is another acid, both are the hydroxy and acid. It is a diester, cyclic diester. So the acid we have taken is a lactic acid, common name. So therefore lactic acid almost doubles giving the diester, cyclic diester is formed, which is called a lactide, Similar the reaction we have in the amino acids also. Alpha amino acid, when you do the pyrolysis, why I am giving the reference means comparative study generally will have the closer observation. So the NH and the C double bond O. This is a cyclic diamide, cyclic ring. It is NHCO means amide, it is. Cyclic diamides are called dipepperagines. So in this first case we call lactide, here it is called dipepperagine. If this is alpha, first case is alpha hydroxy alpha amino. If the beta hydroxy, that is COOH, the OH is on the then next carbon, that is called alpha beta. If a beta hydroxy is taken on heating, both beta amino and the beta hydroxy both have the similar type of the reaction. Removal of the HOH, because the hydrogen shows some hyperconjugation with the acid, the hydrogen shows here also. So ammonia molecule is removed, water is removed, both will give what? Alpha beta unsaturated acids. alpha beta. Therefore, you call it as a alpha beta unsaturated acid. Unsaturated acids are formed. This is same with the case. Even beta hydroxy amino acids also will have the same type of the alpha beta unsaturated acids are formed, right? Whereas if the gamma onwards, gamma and onwards also you can take it as a commonized onwards. If gamma or delta amino acids are there, the hydroxy function will make a gamma hydroxy. This internal reaction takes place between the OH and HA. This gives this 4 carbons plus 1 oxygen comes in the center. So, you will have a like this structure. So, this is a cyclic ester. Cyclic ester is called a lactone. Cyclic esters are called lactones. Whereas if a gamma amino acid, if a gamma amino acid is taken and heated, just heating, that's all, then amino and COOH, they are enough distance. Therefore, you make get a 5-membered ring with the 4 carbons with the a carbonyl group and with nitrogen coming in the center. So, this is the extension of the acid, but this type of the cyclic amide, this is called cyclic amide. Cyclic amides are called lactams. So, the nomenclature, remember what is lactam means cyclic amide. Which of the following amino acid will give a lactam on heating? Beta amino acid, gamma amino acids will give lactam. Beta amino acid will give the unsaturated acid. Alpha amino acid similar to the lactic acid, here lactides, here it is called dipepperagine. Dipepperagines, it is a cyclic diamide, it is nothing but a cyclic diamides are going to form. So, these are all just by heating, called pyrolysis reaction, very close to the hydroxy acids property, and 1 or 2 questions have appeared in this particular area also. Now, let us take some points on the specifically protein. Proteins are defined as a polyamino acids. Polyamino acids. So, we have seen already amino acid, one amino group and acid group containing molecules are called amino acids. These amino acids go on react and will give the, let us take a R1 containing amino acid is reacting with the plus a COOH R2 containing amino. We have taken 2 different amino acids, let us call A and B. These 2 are joined now. What happens means, first as a first step, this NH2H and the OH of the acid is removed as a water, and you will get a bond called a NHCO bond. This NHCO bond is technically called amide bond, chemically called amide bond. When it becomes into a protein which exists in the biological species, the same bond we refer as a peptide bond. Same bond we call peptide bond, amide bond or peptide bond. Now, this side party will be the same CH and the R1 and the COOH. So, the molecule obtained by the just 2 amino acids, you call it as a dipeptide. Dipeptide. Like that, one more amino acid, let us say R1, R2, one more amino acid containing R3 is joined, or same one, R1 you can take, R2 you can take, you will get a tripeptide, and so on, several numbers if you add, you will get the polypeptide. So, huge number of molecules go on joining, you will get a large linear polymer which is called a polypeptide. Now, the questions are coming on this area is, a dipeptide will have how many amino acids? 2 amino acids will be there. How many peptide bonds? Only 1 peptide bond. A dipeptide will have a 1 peptide. A tripeptide will have the 3 amino acids. The tri refers to the amino acids, not the peptide bonds. a tripeptide will have how many peptide bonds? Only 2. 3 amino acids are joined, the junctions will be only 2. Similarly, let us say a hexapeptide will contain the 5 peptide bonds. If you hydrolyze a pentapeptide or a hexapeptide, let us say hexapeptide is taken, the peptide bond can be hydrolyzed by adding the water in presence of the acidic medium. So, one water H and OH is added, reverse reaction, that is addition of water will give back this one. So, each peptide bond to hydrolyze, one water is required. So, hexapeptide to give this amino acids, how many amino acids are formed? The question is 6, N will be 6 here. How many peptide bonds are there in the hexapeptide? Only 5. So, therefore, how many water molecules are required? This N also can be questioned. If this is the question, N answer is 6. A hexapeptide on hydrolysis gives 6 amino acids, or it will contain 6 amino acids. It required how many water molecules? This N is equals to only 5, because 5 peptide bonds are there. Recently one question has come. So, on hydrolysis concept, a peptide hexa or heptapeptide is taken and hydrolyzed, it consumes how many water molecules to give the amino acids? Means each peptide bond require 1 water to hydrolyze, isn't it? So, remember that a tripeptide will have the 3 amino acids and 2 peptide bonds. Like that, a polypeptide will have n number of amino acids, n minus 1 peptide bonds. N number of amino acids are there in the polypeptide. How many number of peptide bonds are there? Means simply n minus 1 will be the peptide bonds. In the concept of protein synthesis, let us talk about a dipeptide preparation. I want a dipeptide. So, one amino acid A is a alanine and B is a phenylalanine. When I add these two and react them, a dipeptide is going to get because this is one amino acid, this is another amino acid, dipeptide. How many types of dipeptides are going to form? Means answer is A may react with A, giving AA, B may react with B, BB, A and B may react, B and A also react, and these two are not same. AB is not same with BA. For example, if somebody wants only BA, not AB, how to prepare BA? How to prepare BA is now a question. That is called the protein synthesis. To want a specific BA, what we have to do is, you take the phenylalanine. Phenylalanine is nothing but a phenyl containing a COOH and amino group. So, a phenylalanine means now this COOH should react with the amino of this one. So, phenylalanine, what you do is this amino group you treat it with a blocking agent like phenyl, that is benzoxy, oxyl chloride and so on. Different types of the blocking agents are there. You add this blocking agent to this phenylalanine, so that this NH will become a blocked, and this COOH is converted through using the either the thionyl chloride or PCl5, make it as into a COOH. So, phenylalanine is now the amino group is blocked and a big blocking group has come, and the COOH is activated into the COCl. This is what your phenylalanine. Now, you add this ordinary alanine. Ordinary alanine will have the COOH and NH2. Now, the acid group is activated, so therefore, it readily reacts with the amino. Instead of amino reacting with the acid, so acid chloride reacts with the amines fastly. The reactivity of acid chloride side is very high. So, therefore, you get this the B joined with A. So, a specific type. Later, by mild reducing agent, the block can be removed. So, B and A type of, like that, a series of amino acids, if you can identify what is the amino acids in that particular series, one after the one, you block the first compound and activate it and join it. Again, activate the COH and join the third compound, fourth compound, and so on. A big series of the desired the amino acids may be joined to prepare a polypeptide. Now, let us take 1 or 2 points on the structure of a protein. The structure of protein is divided into the 4 levels. The first one is level 1, or it is also called a primary structure. Primary structure. The primary structure, A is linked with B, linked with, let us say, H, linked with S, linked with Q, and so on. This is a 5-membered amino acid pentapeptide containing the A, B, H, S, Q. These are the different amino acids in this particular order is linked. So, the order of the different order or sequence of the different amino acids is known as the primary structure. I know the primary structure of this, let us say, a hormone called what you call insulin. Insulin contains around 13 amino acids in a particular sequence. I know the primary structure of insulin means what are the amino acids, in what sequence it is joined is called the primary structure. Knowing the sequence and what amino acids and in what sequence they are arranged is known as what? A primary structure. Sequence or order with different amino acids is called primary structure. However, in the syllabus it is only the one is given, but let us take 1 or 2 points on the secondary and primary and tertiary also. Secondary structure. Secondary structure means the amino acids, actually some millions of molecules will be joined. So, maybe if the length, if you calculate, it runs to so many meters and meters. But in a one simple that is in a cell, how they are adjusted means the amino acids, after getting the long, they go on coil up like this, right? They go on coil up just like a spring. Now, what is the width of this coil? That is called width, and also the height. Both are decided by the where these amino acids are linked. One stretch having a CO, another stretch having the NH will have a hydrogen bonding. So, through this hydrogen bonding, these strings are attached. So, that decides the width of this string and also the height of the string. So, therefore, how beautifully they are arranged is now the secondary level is due to this particular structure, that is hydrogen bonding is the responsible for this one. In the primary structure, no hydrogen bonding is involved. So, therefore, if you heat a certain extent, the hydrogen bondings open up, but whereas the primary structure will not open up. Therefore, under normal temperatures, the hydrogen bonding works excellently, optimum temperature. Beyond that optimum, the second level will be destroyed. Primary level to destroy, you need very, very high temperature. So, primary level of the will not be destructed, but the secondary, third and the tertiary, level 3 is called tertiary. After getting these coils, so many coils will be goes on spin up around a middle one, or sometimes no middle one will be there, but to see it looks like a big rope, and one string goes on spinning also. So, what are the forces which is acting means once again the hydrogen bondings between the side by 2 springs. So, hydrogen bonding is there. Another one is spinning. So, one goes round around this one. If you pull this one, it will not come because it is encircling the middle one. If nothing is there, also they go on spin up like this. Therefore, these are the 2 main forces which are making the molecule. It is the single molecule. It goes round and then goes up and then comes down and goes up. This is all single molecule. It is not the different 6 pieces are not involved. This goes up and come down and goes up and come down like that. This whole molecule is only one molecule. This is called what? Tertiary structure. Now, the level 4. Level 4 is a quaternary structure. Quaternary structure. The tertiary, secondary and tertiary and the quaternary, all these three involve the hydrogen bondings. Once again hydrogen bonding will be the once again involved. Let us take, we have purchased a 3 kgs of such a particular big type of the rope and we put it in a corner of a room. Now what will be the shape that occupy? The shape of that rope may occupy, finally physical shape may be like this, and where in a particular cave type of the structure is the formed, into that cage a molecule, let us say a capital D molecule enters. Capital L compound, its mirror image actually, D and L are mirror image. If D is permitted, L is not permitted, because the cage is also 3-dimensionally prepared. So only dextro molecule will enter, set into that cave and becomes into 2 pieces. Sometimes 2 molecules will enter and join up. So all this enzymatic action, all these enzymatic actions are so specific, that's why only one enzyme will catalyze one molecule. For every molecule, different enzymes are needed. That's why the enzymes will have the temporary structure. This quaternary structure is not a permanent structure, just like a cloud in the atmosphere goes on take the different changes. The quaternary structure, within a second there will be another structure will be formed, so that at that time a molecule will be inserted and breaks down or joined and comes out. So enzymatic actions are so fastly taking place because of that particular quaternary structure. All this second, third, fourth are based on the mainly on hydrogen bonding. So therefore you require the optimum temperature. Optimum temperature. So the biological actions required optimum temperature, specifically Y means the hydrogen bondings retains at optimum. Beyond that certain temperature, high temperatures in the summer, we take that proteins will become the spoiled, that is hydrogen bondings opens means it's a spoiling of the proteins is called denaturation. That leads to the malfunction of the proteins and immediately we get nausea or something like the symptoms will be appeared. However, primary structure will only last when proteins are overcooked, like fried up and all that, primary structure will be lost, but the secondary and tertiary will be lost just crossing the optimum temperature, these will be lost. So therefore the hydrogen bondings are responsible in these 3. Chemical bond, peptide bonds are responsible for the primary structure.